Hello, everyone. So my name is Mathieu Febvay, and I am a PhD student at the ERIC laboratory of University of Lyon in France. It's 11:30 p.m. here, so it's night, like Ricardo, I think. So Ahmed and I are working on the optimizing inference on a resource-constrained device, and especially for the healthcare industry. So in this presentation, I'm going to present our work, which are an evaluation of deep learning frameworks for image classification on resource-constrained device. So today, many mobile applications use artificial intelligence in diverse ways, such as gaming, social media, artistic filters, or augmented reality. And they use AI. When they use AI, they are using different tasks like face detection, object detection, or real-time image classification. And these models, when they use AI, they use complex and millions of parameters, and they need a lot of computational resources, mainly given by the cloud today. And for users, when they use cloud technology, it means three things. So the first one is that they need a mobile connection to send their data to the cloud, and the latency of the network is not negligible. The second one is that they send information that belongs to them, and that information could be personal. So there is a privacy concern. And the third one is that the cloud is not free. There is a cost, and it could be expensive. So this is why on-device inference is an alternative, protecting data, fixing loss of internet connectivity, and reducing computing costs. But recent improvements made on hardware like neural and tensor processing units, which are called NPU and TPU, or digital signal processor, DSP, and other accelerators, let machine learning and deep learning on-device execution possible. Several mobile and deep learning frameworks have been developed by open source community and industry leaders with the low-level software optimization like general matrix multiplication, which is GEMM, GPU libraries with OpenCL, Vulkan, and OpenGL, and most recently, general hardware accelerators API, such as NCNN API or ARM machine learning framework. But unfortunately, these features are implemented differently in the frameworks, and combination of a model, a framework, which hardware is running on, and devices make performance assessment difficult. So our approach is to evaluate frameworks and models designed and developed for mobile devices with the goal of providing the community or inference latency evaluation and results, and power efficiency results of different models, allowing scientists to take the proper decision and save their time when choosing software libraries and hardware when they run image classification or object detection or instant segmentation on resource-constrained devices based on ARM Cortex-A architecture. So for our experiment, we chose two smartphones, which has a system on a chip, a SOC, and two smartphones, so they have a generation gap, and we shows one tablet with a boosted stock. So we selected the latest Samsung Galaxy Tab S7, which is in the middle of this slide, and which contains a Qualcomm Snapdragon 865 Plus. We shows also the OnePlus 8 with the Snapdragon 865, and the last, this is not the last, but the previous generation as today, for today, this is the Galaxy S21 with the Exynos 2100. So that's our three devices. So the two Snapdragon are on the same architecture to explore if the extra boost provided by the 865 Plus produce a significant impact on the latency. The Exynos 2100 represents a generation gap with the Snapdragon, and it's based on the new Cortex X1. So our experiment was launched on all the hardware available on each device, which was the CPU, the GPU, and NPU, with different ePress rating scenarios. So for 1 to 10 thread, but we'll see that later. And when we run on the GPU, we inferred with OpenCL, OpenGL, or Vulkan graphic libraries. And the manufacturers, they consider that the CPU, GPU, and NPU, they consider all this hardware as a whole, which is named the AI engine. And this is the one where when the user use NN API, that's the AI engine that it runs. So we test 4 open source frameworks, which was TensorFlowLite, MNN, PyTorch Mobile, and NCNN. There is others like TFLite or TNN, but we only focus on the 4. They all have ARM optimization and OpenNP library integrated in the source code. TFLite was, at the time of the paper, the only framework to have a general hardware accelerator library, which is an API, which allow inference on the AI engine. And we selected these frameworks due to their mobile context, and all of them are compatible with Android and iOS. The inference was launched on the ImageNet dataset, validation subset, on the pre-trained models, because they are commonly used as backbones for image segmentation. So the main difficulty in this paper was to find common models available on both PyTorch and TensorFlow, but we managed to find 5 32-bit floating point model and 2 quantized models. So here are our models. So we have the same for both training frameworks. So we have SqueezeNet, MobileNet, Inception, the ResNet V1 series, and we have the accuracy, top 1 and top 5 for image classification on ImageNet. And we see that SqueezeNet and ResNet series are more accurate on PyTorch, and MobileNet and Inception are more accurate on TensorFlow. So the frameworks used for experiment, they can't execute the download models. They have to be converted before. TFLite and PyTorch Mobile were the easiest to switch because the tools provided by the training framework are easily available, And so you can switch from TensorFlow to TensorFlowLite and PyTorch to PyTorch Mobile easily. But MNN and CNN, they don't support all of the model operation. So there was some issues during the conversion. And we need to convert first PyTorch models to ONNX before converting the models to MNN and NCNN, which is not the case for TensorFlow. So during the training phase of models on TensorFlow or PyTorch, each image is transformed to fit in the input tensor. So we had to reproduce the pre-processing steps to have the best accuracy. So as you can see on the left, TensorFlow need to crop or pad the image, then to scale the image down, then to normalize each image color channel, red, blue, and green, with the mean and standard deviation for a different model. So FP32 and Quantized models. And for PyTorch, that's the opposite. It resizes the image first, then it crops the image. And there is other parameters for normalization that are not the same compared to TensorFlow. So for each framework, we developed a Java hybrid application which looked on all the converted models and infer each of the ImageNet validation subset, which is 50,000 images. And we did it for each hardware available, like I said, CPU and GPU and NPU. And we did it for 1 to 10 threads. At each inference, we record the time elapsed by the device to output the probabilities of the image. And we compare the result to the image key contained in the ground truth file provided with the dataset to know if the highest probability and the 5 best were in the results. Then latency and accuracy are saved in a CSV file on the internal memory. The energy consumption was not measured in the first phase of the experiment. We did it in a second time. And in addition, in the second phase of the evaluation, we record the screen and camera power consumption separately to isolate the hardware used during the inference. So the results are here. So we have an acceptable latency for an acceptable latency image segmentation. In real time, we need a time under 30 milliseconds. So we kept the best latency for each device and each model in this results. So TensorFlow model latencies, as we see here, are the best with TFLite OpenCL for floating point models. And we also see that Snapdragon 865 Plus outperforms the most recent generation due to its better CPU and GPU frequency. But it is not only due to this, as we will see later. And for small models like MobileNet, there is a small improvement from TFLite OpenCL to NNAPI. But for larger ones, such as Inception, the latency is reduced from 25% to 75%. So there is a huge gap. So when you infer on a mobile device using CPU, there is a protection called dynamic voltage frequency scaling, so DVFS. And when you do that, this phenomenon is triggered. So these charts represent the raw inference made with NCNN on the Snapdragon 865 with one CPU thread through the whole dataset. So on the top, we infer with inception with V3 PyTorch model, and below we have ResNet 50 TensorFlow model. And we clearly see that the DVFS phenomenon with the ResNet 50 model inference, which is below. And one way to simplify this raw chart is to use the kernel density estimation function displayed at the right. And when you have the DVFS mechanism, you have two modes instead of one. So this is a picture below on the right. So these charts are another example to quickly resume how the CPU behaves. We clearly see that SqueezeNet is performing well on CPU with two threads because of its mode, which is very tight. This is the second picture on the right from the top here. And if we look at the GPU when using TensorFlow-Lite, OpenCL, we can see that the number of threads does not influence the inference. They are all the same. We also see a single mode for each chart. There is no frequency scaling. So we can say that the higher is the temperature, the quicker the DVFS mechanism will trigger. So as I said, Snapdragon 865 Plus outperforms the most recent generation due to its better CPU and GPU frequency. But if we look at the size of the devices and the design of the motherboards, we see that the tablet can dissipate more heat than the others, which means that the Snapdragon 865 Plus will trigger the DVFS later, even if its CPU frequency is higher. It has an impact on CPU and NNPI performance. So an accuracy loss occurred when the model is converted. For TensorFlow models, there was a drop of 1 to 2% on top 1 and 2 to 3% on top 5 for all frameworks. And the same figures appeared for PyTorch, except for NCNN, which has a huge drop with 7 to 13% on top 1. And in addition, SqueezeNet, ResNet 50 and 11 from TensorFlow were not operating. So the pre-processing parameters provided on TensorFlow Hub, leading to an accuracy cap. That's why there are grade on the picture. And the accuracy loss from the Quantized model is negligible regarding the latency gain. MobileNet V2 lost 1.89% compared to its floating point version, but it's reduced its latency by 5% on the Exynos. So I almost finished. Sorry, I'm a bit late. In the second part of evaluation, we record the elapsed time for the device to go from 100 to 97%. With the help of battery historian software from Google. We measured the screen consumption, like I said, by setting the device in plain mode and recording the time for the device to reach 97%. So then we measured the camera consumption with the same methodology. And you have below the screen and camera power consumption. And we have the results in these figures. So the Snapdragon 865 Plus screen is bigger than the two others. So and the Exynos 2100 has the most powerful camera module. So that's why the results are not the same between the three. And the screen and camera have a bigger impact on energy compared to the dedicated inference hardware. So they consume more battery than the CPU or GPU or NPU. So in this paper, we present an inference latency benchmark on mobile to help the community better deploy image classification or segmentation model on Android devices. And our results show that quantized models on AI engine are more energy efficient and performs better than floating point models with a tiny loss of accuracy. And TFLite provides an easy model conversion and integration process. PyTorch does it as well, but it needs to support GPU and NPU. And it seems that its support is going to be integrated in PyTorch 1.10, which is now in beta version. MNN and NCNN integration inside Android application is not a straightforward task. The configuration step is not user-friendly, as engineers need to compile and or find the appropriate converter and execute commands to transform the original model. And finally, manufacturers should improve heat dissipation or cooling mechanism on small devices to improve the DVFS effect to reduce it. And thank you very much.